Greetings, AP Chem. Today we are going to be talking about Hess's law. So Hess's law, I would say, is more of a theoretical exercise than something you maybe are going to do in real life. You could do it in real life, but it's kind of like a neat little party trick, I think, more having to do with enthalpy changes than anything. And the general idea behind Hess's law, it plays off the fact that enthalpy is something called a state function. So it's not really important that you know what a state function is, but I'll give you the quick and dirty version of it. So if you think about going from point A to point B, the difference in distance from point A to point B is from here to here, right? Okay. So a state function is something where it doesn't matter how you get from A to B. It's just that the difference from A to B is a number. So if you think about enthalpy changes, it doesn't matter if it takes me 5 steps to get to one situation to another, or if it takes me one direct step. It doesn't really matter. What happens is that enthalpy change is still the enthalpy change and it doesn't change. Whereas like if you think about an elevator, if I go from the top floor to the top floor down here, if I go from the top floor to the bottom floor and I think about the difference in change, it's not like the amount of energy it would take me to go through an elevator versus the stairs. So if I go down the stairs, it's going to take me more energy. If I go down the elevator, it's going to take less energy. All that matters is the difference from start to finish. So what happens is because of that, there are some little tricks that you can use to figure out enthalpy changes, even if you don't actually know the enthalpy change for your specific process. And Hess's law is that. So what Hess's law does is it gives you, I'm going to quick scoot ahead for a second. What Hess's law does is it gives you what I call a goal equation. Now, if you think about this top equation here as a goal equation, that is the thing we are trying to find the enthalpy change for. And what it does is it gives you processes that when we do some mathematical manipulation, give me my goal equation. And so there's different things that we can do to these equations to get them and manipulate them to be like this goal. And so when we go through those questions, there are, like I said, some things that I like to ask for each equation. And out of context, these are not going to make that much sense, but the examples I think will really clarify things. So I guess just write down these rules, and then as you go through the examples, then it'll make sense. So what I want to do is think of my goal equation as the parts I need to find within the puzzle of the other equations. So when I look at any reaction that I'm trying to use to make my goal equation, I ask myself if there's any compound I need in this equation in my final equation that I can't find anywhere else. And I say that because, as you know, with balancing, things like oxygens and waters and carbon dioxides, they can cause us problems. So what we look for are things that aren't those things usually, and they're going to help us out. So we're going to zone in on that thing that we can't find. And if we can manipulate that correctly, everything else should fall into place. And it's pretty cool. So what happens is if I find something that I need, I ask myself the next question, is it on the correct side? If the thing I need in my final equation isn't on the correct side, what I'm going to do is I'm going to take my whole equation and flip it so that my reactants are my products and my products are my reactants. When that happens and you reverse the reaction, you change the sign on the enthalpy value. So a negative becomes a positive and a positive becomes a negative. And if you think about an energy diagram, that should hopefully make sense. Then I ask myself, is it in the correct quantity? So is it in the right coefficient that I need as well? If it's not, you can multiply or divide the equation to get it to the right coefficient, but you have to change every coefficient in the equation. So if you decide to multiply everything by 2, every coefficient gets multiplied by 2. And so does the enthalpy. And this should hopefully make sense too, because if I have twice as much stuff reacting, I should get twice as much heat like we talked about. Okay? What you do is you go through that process for every equation that you're given to build your goal equation, and then things that are identical on opposite sides of the equation cancel out. And you do have to watch for phases sometimes, so be careful with that. Things that are on the same side add up. And then what ends up happening is if you manipulate your enthalpy values correctly as you go along, all you have to do is add them up, and that'll give you the enthalpy change of the reaction. So like I said, it's kind of like picking and choosing the stuff that you want to get out of the equation, and it'll give you the enthalpy change, because if we know the enthalpy changes of those processes, they kind of add up to the process you're looking for. So I'm going to go through 3 examples, and actually I'm going to go straight into my notebook this time. Unlike normal, we go into the examples and then we'll copy them down. For this one, I think it's just going to be easier, so there's not quite as much transferring. So what I would, I'm going to walk you through this one, and then I don't know if you need to copy this one down. That's kind of up to you, but then you can pause the video and copy them down as you go along. So if we look at this one here, this is my goal equation. So I want to make H2 and half O2 gas, and I want to make H2O liquid in this situation. So in my first equation, what I want to do is I want to find something in here that I need for this final equation, and I want to manipulate that and see what's happening. If we look at this, this is not the correct final equation because it's got H2O in the gas form, and I want H2O in the liquid form. So what we're going to do is we're going to zoom in on something that is something I can only get in this equation that I need for my final equation. And if you look here, I need H2, and this has H2, and I cannot find hydrogen gas in any other equation. So I'm going to zoom in on that, and that's going to be my area of focus. I would generally not recommend doing anything to oxygens, because oxygens are our problem children. So do not do anything with those. Okay, so if I do that, H2, I'm going to ask myself the series of questions that I did before. So I find this thing, then I ask myself, is this thing on the correct side? So if you think about this problem for my goal, it needs to be a reactant, and in this equation here, it's already a reactant. So yes, it's on the correct side. The next thing I ask is this thing in the correct quantity? And if I look at it, I need 1, and this is 1, so I'm good to go. So in this equation, I'm not actually going to do anything. I'm going to leave it alone, okay? Oxygen hopefully will take care of itself. This H2O gas, if we do it right, will take care of itself as well. Okay, so I look at the second equation then. If I have H2O gas and H2O liquid, what I'm looking for is something that I cannot find in any other equation that I need in my goal equation. And if we look, it's H2O liquid here. So H2O liquid is what we're going to be paying attention to. This gas is not important right now. So I'm going to look and I ask myself the same questions. Is this on the correct side it needs to be? Currently a product, and I need it to be a product, so that's good to go. Next question is it in the correct quantity? Coefficient of 1, coefficient of 1, we're good to go. So I'm not going to do anything for that at all. And then here's where the magic happens, hopefully, if we do this right, okay? Because, I just want to go back for a second, because I didn't make any changes to my equations, I'm going to leave my enthalpy here as well. Now, if I would have to manipulate these equations, I suggest rewriting them. But since I didn't have to do anything to either of them, then we are going to leave it. But always, otherwise, I rewrite everything. It gets messy otherwise. Okay, so what we do is we look at our different sides of the arrow, and normally I line these up, but if you don't want to, you can kind of draw a line like that. And what I'm looking for are things that are identical on opposite sides. And they can be in different equations. So here, H2O gas is a product, and on the second equation, H2O gas is a reactant. And since I have identical amounts, they cancel each other out. If this would have been 2 H2O and 1 H2O, we could have canceled out 1 water, and you'd be left with 1 on the reactant side. And if you look, nothing else is identical and can cancel out. So what we have left is H2 gas plus half O2, and that turns into H2O liquid, right? So I have my equation that matches what I'm trying to make, and then what I have to do is I have to add those two things together and get my enthalpy. And so my enthalpy change is negative 285.8 kilojoules. All right, so that's example 1. Now, we're going to try example 2 here and then see how it goes. So if you want to write this down in your notebook, now would be a good time to pause, and then we will go and dig into this problem. Okay. All right, So this is our goal equation. We're going to start off the same way we did before. Looking at the first equation here, is there something in this equation that I need that I can't find anywhere else, and it's not in any other equation? And again, don't do oxygens if you can avoid it, because oxygens are annoying. Hopefully you're seeing right here that I need a CH4, and there's a CH4 in here, okay? So because I might have to do some manipulation, I'm going to rewrite these down below. So if you look here, I've got CH4, and I ask myself those same questions. Is CH4 on the correct side that it needs to be here? Yes, they're both reactants, so that's good. But I will ask myself then, is it in the correct quantity? And in this case, it's 1 for coefficient, but in the goal equation, it's half. So what I need to do in this case is I need to divide every coefficient in this equation by 2 to get this to work out. So if you look, and I like to do this off to the side here so that I keep track of what I'm doing. So I'm going to divide all these coefficients by 2, and I'm going to rewrite it. So I've got half of a CH4 gas plus O2 gas, and that turns into half CO2 gas and H2O gas. Now, as a consequence of that, I need to divide this enthalpy value by 2 as well. So my enthalpy value is negative 280.26 kilojoules now, because I'm reacting half as much. Okay. So now I'm going to look at this second equation here, and I'm going to play around with this. So if we look, the H2O that I need in my goal equation is a liquid. This H2O is a liquid on is a liquid as well. So this is what I'm going to zoom in on. This one here, I'm not going to worry about. I only worry about one thing that I need to take care of. And then it's kind of cool. The rest of it should just take care of itself if we can find those things that we can't find anywhere else. So if I look here, I look at H2O liquid and I ask myself, is it on the correct side? And in this case, no, it's not. So I know already I'm going to need to flip it. And I ask myself, is it in the correct quantity? In this case, yes, because I have coefficients of 1. You can flip and multiply or divide in these situations. So I'm going to flip this one. And what I like to do to make my work a little easier to follow is I line up all my arrows together. So when I flip that, I'm going to take H2O gas and put it on the product side. And then I'm going to have H2O liquid and have that on the reactant side. And a consequence of doing that is that my enthalpy change, which was a positive 44, flips to a negative 44 kilojoules. Okay. All right. So here is hopefully the moment of truth. We want CH4 to be there, and then we'll see what cancels out. So if you think about this as like a dividing line here, H2O gas and H2O gas go away, and everything else here is not identical, is unique, and so we're going to keep that. So it's 1/2 CH4 plus O2, and that turns into half CO2 plus H2O liquid. These phases are important when you have different phases. If they don't, it's not such a big deal. So to deal with this, you're going to add these together here. And so my delta H is going to be negative 324.26 kilojoules. Okay. These are simple ones. So we're going to get into a little more complicated one for your third problem. But I think you can do it. All right. So here's what I want you to do. I want you to see if you can do this one on your own. Target something that you need, get it in the correct side, get it in the correct amount, and then we'll see if you can figure it out. All right, so pause the video and give it a try. Did you pause it? Did you really pause it? I hope so. Okay. So my goal equation is this here. I'm going to look in this first equation, and I am going to target something that I can only find in one place. If I look here, I have C2H6 gas, and I don't see it in any of the other equations. There is all of this nonsense here. And when you look at that, you're like, oh man, this is going to be a problem. If we do it right and get the stuff we need in the correct quantities, it's not going to matter. So we're going to target the C2H6. So ask yourself the 2 questions. Is it on the correct side? Yes, it matches the side I need it to be on. Is it in the correct quantity? No. I have 2 for my equation that I'm working with, and I have 1 for my goal equation. So I'm going to need to divide this by 2. Everything in here gets divided by 2. So let's check it out. We've got C2H6 plus 3.5 O2. You could write that as like the half as well, but the halves kind of bother me a little bit. And then I have 2 CO2s and 3 H2O, okay? Now, I don't have any like phase change flips or anything happening here, so I'm going to leave these off just to save a little bit of time. So I have those, and because I divided by 2 with my reaction, I've got to take this enthalpy and divide it by 2 as well. And if I do that, I get negative 1,559.7 kilojoules for that one, okay? So I've taken care of this C2H6. This should all just magically disappear if I do the rest of this right. So let's look here. Next equation, I've got C2H4 plus O2, and it makes CO2 and H2O. Okay. I need C2H4, so I ask myself the questions. Does C2H4, is it on the correct side? Yeah, I was going to say yes, but no, not so much. It's on the wrong side. So I need to flip it. Is it in the correct quantity? Yes, because I have coefficients of 1. So what's going to happen then is I need to just flip this, and then we will do our magic here. So I'm going to line my arrows up, and I'm going to bring all of my products to the reactant side and vice versa. So I've got 2 CO2 plus 2 H2O, almost forgot it there, and that turns into C2H4 plus 3 O2. Now, because I flipped that, my enthalpy change turns positive, and it's going to become positive 1,410.9 kilojoules. Okay, so I've dealt with that. Notice I have not paid attention to the O2s and the CO2s because, again, if I do this right, it should just work itself out. All right, last one. If we can find something in here, hopefully. We need H2, and we've got H2 here. So we ask ourselves the questions yet again. Is it on the correct side? No. Is it in the correct quantity? No. So I've got to flip this and divide by 2. Okay. So I'm going to do that work here. So I've got H2O, and then I've got it turning into hydrogen and half of an oxygen, which I'm going to write as a 0.5 O2. So when I do that, I need to change the sign, and I need to divide it by 2. So it's going to be a positive 285.83 kilojoules. So sneak it in there. Okay. And now is where we cross our fingers and hope that this went okay. So think about what we need. We need C2H6, I need C2H4, and I need H2 to show up, and the rest of this needs to go away. So if you look at this, let's figure it out. I currently have 2 CO2, and I have 2 CO2 on the product side. They cancel and go bye-bye, okay? I have 3.5 oxygen. And here I have 3.5, and so that goes away. And then if we think about water, I've got 2 and 1, which adds to 3. And here I've got 3 waters, and all is right in the world. So what I have left is just what I need for my goal equation. And I did not waste my time thinking about any of that. So it's C2H6, and that turns into C2H4 and H2. And then my enthalpy change for this whole shebang is going to be a positive 137.03 kilojoules. Now, is this the most straightforward way to solve your problems? No. Is it kind of nerdily satisfying? Yes, for sure. What you'll see is that you will see them do this on a multiple choice test. It's really easy to do. It's not this complicated. They will give you much more simple formulas, but this is the general gist kind of behind this. And this will work with enthalpy as well as some other types of processes, which we will get into later. So if you find yourself having questions, please make sure you get them cleared up, and we will talk about them in class. Good luck.